Hi, welcome to this particular module. In this module we will concentrate on the practical aspects of the DC speed controller. In the last module, if you remember, I have discussed the details quickly, right, about how we can design DC speed controller, and in this module I will ask my TA to further show you the experiment part. He will discuss little bit about what is the importance of that circuit, as we have earlier prepared it for you guys, and if you have any questions at the end of the module, you can always ask us through forum. I will ask now Sitaram to take it over.
Now we will discuss about the implementation of speed control of a DC motor using operational amplifier. As professor already discussed in the last module, the complete working of DC motor, and he has also discussed about why it is required and how the speed control has been implemented. So in this module what we are going to see is that we are going to develop a signal conditioning circuit as well as a controlling unit in order to control the RPM of a motor, but the complete case study is building using operational amplifiers. So the major task of this particular session, this particular case study, is that first we will develop the signal conditioning circuit that is required for a sensor to convert the digital pulses into the analog output and to map with respect to the output of encoder to the input of set point. Then since we are driving the motor by using operational amplifiers, as op amp cannot directly provide enough current in order to drive the motor, we also have to design a driver circuit in order to use the output of operational amplifiers as well as to run with the help of the output provided from the operational amplifiers. So first we will discuss about how exactly the driver circuit looks like, then what is an importance of having an signal conditioning circuit for the sensor, and how exactly we are going to convert the digital pulses that we are getting from the encoder to the analog linearly varying output that match with respect to the input of your set point. Then later on we will see the working of each controllers, starting from on off controller, P controller, PI controller. Then we will also interface all the blocks, all the subsystems that we have designed in order to make a closed loop control system. We will integrate everything and we will see the demonstration of working of each controller with respect to different set points that we give it. Right. So this is the complete overview of this demonstration. So as professor already discussed about the closed loop control system, so first part what we have to do here is that we have to design this particular block, which is an error detector. We will see how exactly we do that error detector using operational amplifier. Then we will discuss about the importance of having different controllers, how we do using operational amplifiers. So basically if you look into this closed loop control system, whatever the user require, so in this case user require in the sense what RPM the motor has to be rotated, that we should know. So if a user wants to know about if a user wants to control the RPM of a motor to be somewhere around 100 RPM, right. So the input given to the system should be of the required output that user is intended to make the motor to rotate with. But as we are designing a complete analog control system or electronic module, so when we give in terms of an RPM, it is very difficult for a system to understand the units of RPM. So we require whatever the input that is provided to the system should be in terms of voltages. So but how do we convert this voltages to RPM? So we should always have to think about scaling factor. So based upon the voltage that we provide, based upon the chosen scaling factor, which gives you the information about what voltage corresponds to RPM. So, based upon that particular voltage, system will understand that the motor, the user is intended to drive the motor at that particular RPM. So, similarly, when you see the output from the error detector, the output from the error detector, which is nothing but the difference between the system input to the feedback signal in this case is nothing but the output from the sensor, right. So, the difference between these two is nothing but your error signal. The output that we are getting from the sensor should also match with the input scaling factor, which means that this particular mapping factor, but we are not very sure whether the sensor can match with this or not. So, first we have to understand about how the sensor is, the output of the sensor is, how can we map with respect to. So, by designing a signal conditioning circuit, we have to map the output of a sensor with respect to the input quantity. Then both will be in of same units. Then by using a simple difference amplifier, we can make the difference between the two inputs and we can generate an error signal. We will see one by one. Then that will be passed through a controller. Then the output of the controller, which is nothing but a manipulated variable, will be given either directly to the plant, sometimes by using a driver circuit. In our case, since the plant cannot directly drive from the motor output, the motor cannot directly drive from the controller output, we require to use a driver circuit. So, in this case we need a driver circuit. So, drivers, the DC motor or plant contains both driver circuit as well as DC motor, such that whatever the output it gives from the controller, the same output will be applied across the DC motor, but the current will not be taken from the controller, it will through from external power supply. So, we will also see how exactly the design that we are going to do in order to make the motor to work for particular manipulative variable. Then system, in this case is a plant, will rotate at that particular RPM, but how do we generally understand at what RPM the system is rotating? So, we require, since RPM is in another domain, another physical quantity, and the complete system also requires electronic unit, what we have to use is that we have to incorporate a sensor. So, there are different RPM sensors available in the market. So, either rotary encoders or Hall effect based rotary encoders. So many rotary encoders are also there. So, by using rotary encoders, we can convert RPM by interfacing it to a motor. We can convert the RPM of a motor into digital pulses. But these digital pulses entirely depends upon at what rate the RPM the motor is rotating with and how many number of pulses that we are getting per revolution. So, one important thing that we have to understand about the encoder is that how many number of pulses that encoder gives per revolution. That is very much important. Once we know that, then whatever the output we get from out of digital pulses gives an indication of an RPM, but our system require the output also in terms of voltages, that too linearly proportional to the change in the RPM. So, that it map the output of this particular value should match with this value in terms of units, not in terms of magnitudes. So, that both can be easily comparable, but in this case these digital pulses, it is very difficult. So, what we have to do is that we have to build a signal conditioning circuit. So, such that the signal conditioning circuit, which is the output of the sensor will be interfaced to the signal conditioning circuit, which converts the digital pulses into linear voltages. So, that linear, why I am saying linear, because any change in the RPM, linear change of RPM would result in linear change of output voltage. It should always be in same fashion, right. And not only that, not only in the linear fashion, we should also map the sensitivity factor or scaling factor of the system is equal to the scaling factor that we are mapping factor basically that we are setting for system input to, right. So, that means when you look into that, there are so many number of subsystems that we have to design for this particular particular case study. So, one subsystem would be for error detection, one subsystem for the controller, and in this case another subsystem is your driver to drive the DC motor, then one signal conditioning circuit to convert digital pulses to linear output voltage, digital pulses to linear voltage. Then if this linear voltage mapping factor is not matching with our system input mapping factor, again another signal conditioning circuit is required to map with. So, a total of 1, 2, 3, 4, 5, 6 to 7 different subsystems we will be independently designing. Then we will verify the conditions, the working of each and every subsystem, whether it is working as per our requirement or not. Then we will interface one by one, and sometimes during the interface there are chances because of loading effects, there are chances of not functioning as the requirement. So, we also have to see any interfacing errors that occurs, then we have to solve for the interfacing errors. Now, first we will start with error detector. Now we will see about the driver circuit for DC motor. So, as you remember, in case of a DC motor, if I want to change an RPM, two important things that we have to consider is that one is by varying the input voltage, right. So, changing the magnitude of input voltage also changes the RPM of your motor, as well as changing the current. By controlling the current through the motor can also change the motor RPM. But varying the input voltages is quite easy, either by using microcontrollers we can change the input, we can vary the input voltage, and it is easy to drive it. But in case of varying input voltages, we cannot directly interface it to a motor, because the motor requires a little higher current, whereas the microcontroller cannot provide you the enough current to drive the motor. So, that is why we require to go with a driver circuit. Now, even in case of varying even in case of providing different magnitudes of input voltages to the motor, there are two ways. One, by using a pulsating, as professor already discussed in the class, or you can use DC. So, this particular driver circuit, whatever I am going to discuss right now, whatever I am going to design and demonstrate you, does not require a varying signal, but rather than providing a varying signal, we can also provide a direct DC voltages at the input of the system. So, that any DC voltage provided at this particular positive terminal, right, the motor, the output voltage across the motor will also be the same as the input voltage. But how exactly it works? How do we know that the voltage will be the same, and how exactly the importance of each and every block that we are using it here? Everything we will discuss one by one now. So, when you look into the system, recall of our working of our operational amplifier. Since our intention was to use an operational amplifier at each and every aspect of the design. So, when you recall into our operational amplifier, few important properties. One important property is that the positive terminal virtual ground concept, which is nothing but the difference between the two terminal voltages should be always same. But this case will be valid only if the operational amplifier is in negative feedback system. Now, in this case, if you see, when we say a negative feedback, when the output of operational amplifier is connected to the negative terminal of our operational amplifier, then we say it as negative feedback configuration. Even in this case, if you see, the output of an operational amplifier is connected to a negative, but through some resistor, transistor, and the emitter of the transistor to the negative. No matter what, with so many other components, we have interfaced the output of operational amplifier to the negative terminal. So, still it is in negative feedback loop. So, because of this negative feedback, as we know the one important virtual bias concept, virtual ground concept, what it says. So, the whatever the input voltage that we apply at the positive terminal of an operational amplifier, it also maintains to have the same input voltage at the negative terminal of operational amplifier too. As a result, when we apply V1 of different magnitudes at the positive input terminal, the voltage across the motor will also be the same. So, one aspect is whatever the microcontroller. So, that means this particular input we are getting from a controller, whether it can be a digital controller like a microcontroller or microprocessor, or we can design our own op-amp based PPI PID controllers or on-off controllers in order to drive this. So, since our intention was to go with an operational amplifier, say when we are using a op-amp based controllers, say especially PI controllers. So, when this controller gives a manipulated variable, that output will be directly connected to the positive terminal of our operational amplifier. So, as a result, whatever the controller is giving the voltage, the same voltage will be even at the motor terminals. One terminal of a motor is already connected to the ground. So, this particular voltage is also equal to V1, but what about the current that is required to drive the motor, right? Whether is this good enough to drive the motor, everything we have to check it. But before checking everything, first we will understand how exactly this works, where the current is being provided to the motor. So, one aspect of voltage, it is clear that the voltage across the motor will be the same as the input voltage that is connected at the positive terminal of an operational amplifier. Since the output voltage, since the output of operational amplifier is connected to through a resistor through a transistor. So, in this case we are using 2N3019. It is not compulsory that we have to always go with 3019, either you can go with the 2N3055 or even BC5000, but only thing is that it should match the requirement. What is the requirement here? The one thing is that the motor rating. So, in this case whatever the motor that we are using requires a minimum of say 100 milliamps current. So, the transistor that we select should able to provide or should work for at least 100 milliamps of current, right? That is one thing. Then it should not damage. Another thing is the base current, right? So, these things are very much important when we are selecting any electronic component. So, in this case, as we require only 100 milliamps, 2N3019 support for 100 milliamps of current, but if your motor is a little higher rated which requires more than amps of current, we can go with 2N3055 which can support up to 10 amps of current, or TIP35C which can work up to 1.5 to 2 amps of current. So, please look into the data sheet for further information about different properties, electrical properties of transistor. So, what happens now? So, since this particular voltage is of V1, say for example, say the input voltage V1 that we have connected is of 1 volt, this particular value is also equal to 1 volt. So, as a result, suppose if the if this voltage connected is of 8 volt, so 1 volt will be dropped across this value and remaining 7 volts will be dropped across this transistor. But the problem would be, because of 7 volts drop and because of 100 milliamps of current, the total power, the total wattage dropping across the collector and emitter terminal will be 7 into 100 milliamps, which will be 700 milliwatts. So, total 700 milliwatts of power will be dropped across the collector and emitter, and there are chances of slightly heating it, right. And not only that, the current flowing through entirely depends upon the current the motor is being accepted to. So, as a result, to limit our current, what we can also do is that instead of directly connecting the emitter of a transistor directly to the motor, in practical I have used a resistor of 56 ohm of 2 watt such that the maximum current this can allow will be 100 milliamps of current. So, if you see, so if we are applying 8 volt, so the maximum voltage that we are using is a 5 volt and the minimum say 0 volt. So, total will be 8 volts drop across this, and this requires 0.7 volts to switch on, minimum of. So, 8 divided by 56, if you see, the value will be somewhere around 142 milliamps. So, suppose if there is some voltage drop, say 1 volt, so total drop will be in this case 7 divided by 56, 125 milliamps. So, no matter what at what voltage that we are at, the maximum the maximum current that will be at the collector or emitter will be very less value. As a result, the power across the collector and emitter will be smaller. The chances of heating the transistor will also be smaller. And another resistor which we are using it here, which is of 180 ohms, the importance of this resistor is to limit the current flowing through the base of transistor. Of course, TL082 or op amp, any op amp can provide up to maximum of 20 milliamp. Anyway, this is really smaller, but in case when we are directly connecting with some other thing, it should not damage the transistor. So, in order to limit the current flowing through the transistor, by using some current limiting resistor, it need not to be 180 ohms, we can go with 220, 270 some value, so that the current should be smaller. So, two resistors, one 220, other one 56 ohms, but in this case we require to have a little higher wattage at least 1 watt, so that this resistor will not heat. So, as a result, whatever the voltage that we apply at the input of positive terminal, the same voltage will be even across the motor. So, the motor will start functioning. So, the purpose of this diode is called freewheeling. So, when the motor is not working, so whatever the energy is being stored should dissipate. So, in order to when the motor is off, whatever the energy stored will be dissipated across the coils inside the motor, so that it will not damage the transistor. So, this is called freewheeling diode. So, these are the components that we are using it here. Then we have to use an encoder or a sensor to convert this RPM into some voltage. So, for that particular case, we are using encoder. So, the motor that we are using has an integrated with an encoder. For further details of the motor, you can look into the data sheet FIT 0483. So, the motor, this is a micro gear motor which can rotate up to maximum of 155 rpm because of the gear ratio available, and the gear ratio is of 100:1. So, otherwise if there is no gear, the motor will be rotated at somewhere around 15,000 rpm. Since there is a gear ratio, the final rpm will be 155, and the data sheet says that it will give you total of 14 pulses per 1 revolution. So, to understand the working of the circuit, so now what we have to do is that we will create a table. We will give different voltages starting from 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5 and 5. We will observe the frequency of digital pulses by using CRO. Or we can also count how many number of pulses that we are getting, which gives me the RPM. But if we know the frequency of the digital pulses, then dividing the number of digital pulses with 14 gives the exact RPM of our motor. Why we have to divide with 14? The reason is that it gives a total of 14 pulses per revolution. So, that is why first we will vary input voltage, we will provide a different input voltage with a resolution of 0.5, and we will observe the frequency at which the output encoder is giving, or we can count how many number of pulses that it is giving. Then we will divide RPM with 14 and we will see a graph between input voltage and the RPM. So, this gives us understanding about the scaling factor or mapping factor, which means that upon application of 1 volt at what RPM the motor is rotating. Of course, it should be linear. We will also verify whether it is linearly rotating or not, and what its sensitivity factor. So, how do you calculate the sensitivity factor? If you know if you know one particular voltage, what is the frequency or RPM that we are getting, and another particular voltage, say some x1 and x2, say this is y1 and this is y2. So, by doing slope of the line, which is nothing but x2 y2 minus y1 by x2 minus x1, which gives me the slope of a line, this is nothing but a scaling factor or sensitivity factor in this case. Sensitivity. So, once we understand the sensitivity factor, if this sensitivity factor is good enough for us to provide it as an input set point, we will go ahead with this, or we can also change our own sensing scaling factor. We can also provide our own mapping factor, and we can tune complete system to our own mapping factor too. But before that, we should understand the relation between the input voltage to the RPM. For that, now we will demonstrate, we will show you with varying inputs how exactly the output is going to come.